Hi, this is Andrew. Thanks for joining me. This video covers the first part of subnetting using binary. So really what happens when you're looking at subnetting and how binary works and what's happening underneath when you do any of the shortcut techniques to figure out subnetting. This is what happens, and really understanding this can be very helpful. And it's always a good thing to fall back on if any of the shortcuts aren't working the way you expect, or just the knowledge there will help you with subnetting. So first thing I want to do is, and this will be the focus of this video, is covering how binary works. So if we're going to keep it simple, we're going to go with 4 binary digits. And when you're dealing with 4 binary digits, binary is just saying we have a 1 or a 0. So if I go to draw here, my options are for anything. I can have either a 0 or a 1. And if I need to represent anything more than 0 or 1, I need the next place position. And then I'll need the next place position after that. So a single bit can only represent 2 values, 0 or 1. If we have 4 bits, we have more values we can represent. So I'm going to, let's see, turn off drawing, and I'm going to put my values in here, and I'll start at the end. The first position is 1. And let's make everything a little bit bigger here. So if we go home, we'll make it a larger font. So first position is 1. Second position is 2. And all we have to do is just double the 1. The third position is 4. And the fourth position is 8. What we're doing here is very similar to saying if we had the number 296. 6 is in the 1's position, 9 is in the 10's position, and 2 is in the 100's position. So we have 296. Here we're dealing with binary. So we have 4's position, the 8th position, the 4 position, the 2 position, and the 1 position. When we're doing binary, we either have these turned on or off, and it's that simple. If we want to have them turned on, we'll have a 1. If we want to have them turned off, we'll have a 0. So this number in decimal, or in the 10-digit number system, is 1, because we have a 1 in the 1 position and we have no other numbers. Very similar to saying if we had the number 6 in the decimal system, and that is in the 1's position, our number is 6. So now what we can do is say, what if we wanted to go with different numbers? We can say, let's put a zero there, and let's put a 1 here. Now what we have is a 2. So this is a 2 because we have a 1 in the 2's position and a 0 in all the other positions. So what we have is, in the 8th position we have a 0, in the 4's position we have a 0, in the 2's position we have a 2, and in the 1 position we have a 0. So we just add all of those together. So 0 plus 0 plus 2 plus 0 is 2. Now we can obviously change that to be anything else we want. Let's turn that off, and let's go back here. Now if we were to say, let's go with the largest number we can using 4 bits, we would say, what is 8 plus 4 plus 2 plus 1? And that is simply 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. And that means we have a maximum value of 15 in 4 bits. Now, our minimum value is 0 because we can have all zeros here. This might seem very simple, but it's very important to completely wrap your head around exactly what's happening here, because as we expand to 8 bits, and that's mostly as far as we go when we're dealing with networking is 8 bits, we just have some larger numbers, and it's a little bit easier to get mixed up with them. So with 4 bits, we need to be able to go from binary to decimal. We also need to be able to go from decimal to binary. So if we eliminate all of these, and really if you're not completely sure on this, just go in and create as many 4-bit binary numbers as you can. There are only 16 that you can create, but go in and say, okay, what if I put a 1 here and a 0 here and a 1 here and a 1 here. What does that come out to? And that is 8 plus 2 plus 1. Now, it should be obvious, but I'll state it just in case. You cannot put anything other than a 1 or a 0 in these spots. You put a 2 here, that's not binary anymore, and that doesn't work. So just to restate the obvious, you can only have a 1 or a 0. And a 1 means you add that number, and a 0 means you do not. So if we go to a decimal number, so a 10-digit number, and we say, what is, let's make this bigger also. We'll put it on this side. What is 13 in binary? This is something we might need to do. So what do? Well, we just go over here and we say we need an 8 in order to represent 13 in binary. Because without an 8, the largest number we can have is 4 plus 2 plus 1, which is 7. So that's a pattern that exists. Keep that in mind. But we need an 8. So we'll turn on the 1 in the 8, and we'll say 13 minus 8. And that gives us 5 left over. So now 5 is greater than 4, so we need to put a 1 in the 4's position. And we are left, we do a minus 4 on 5, and we get 1 left over. 1 is less than 2, so we don't need the 2 turned on. If we turn the 2 on, we'll go beyond our original 13. So we put a 0 here, and then that means that we have 1 left over, and we put a 1 here. So what does that mean? That means that if we go the other way, we say 8 plus 4 plus 0 in the 2's position plus 1 in the 1's position. That's 8 plus 4 is 12 plus 1 is 13. Now something that we'll really address later on, really important concept. This is an odd number. The only way to represent an odd number is to have the 1's position turned on, because all of the other numbers are going to be even in binary. So if it's an odd number, that means the 1's position is turned on. If it's an even number, that means the 1 position is turned off. So make sure you recognize that, because when we get into subnetting, you'll deal with some numbers, and you want to make sure you see that having the 1 turned on creates an odd number, having the 1 turned off creates an even number. So let's take this to the next step. Okay, so I erased everything, we started over. What I'm going to do now is create a table that has 8 positions. 8 positions is enough to represent any octet, and the octet stands for 8, but any octet in an IP address. So once again, let's go a little bit bigger here. Now here we have, let's do all of them that size. We have in our rightmost position, we have a 1. And then as we saw, we have a 2, then we have a 4, then we have an 8. Now we just keep doubling. 16, 32, 64, and 128. So these are our binary numbers. Now, as we saw before, let's say we had that 13 we were talking about. And we saw 13 is 1, 1, 0, 1. But what happens in all of the other positions? Well, we just have zeros in those, because those are all, if we started at 13 and we're converting, we'd go, it's 13 is less than 128, it's less than 64, it's less than 32, it's less than 16, it is greater than 8, that's where we add the 1 there. So the same process we went through last time. Now, let's start looking at larger numbers. So, let's start by looking at the largest number we can. We saw that with 4 bits, the largest number we can get is 15. So let's put 1s in everything, and we'll see what our number is. So I'm going to add the numbers here. And if we add 128, and let's make them bigger, 128, and we add 64 to that. We get 192. So that's 8 plus 4 is 12, carry the 1, 2 plus 6 is 8, with that extra 1 is 9, and we have 1 there. So simple math. a little bit more difficult to do in your head, but just don't be intimidated by it, is what I'm trying to emphasize. So we add 32 to that, and we get 2 plus 2 is 4, and 9 plus 3 is 12, carry the 1, and we get 224. So now we add 16 to that, and that gets us to 240, and we add 8 to that, and that gets us to 248, and we add 4 to that, and that gets us to 252, and we add, let's try that again, we add 2, and that's 254, and then we add that last one, and that's 255. And that's the largest number we can see in an octet, in 8 bits of number representation, 255. And that goes down, again, starts at 0, goes up to 255. So just make sure you see that is the 128, that's the 64, that's the 32, and we're just adding all of those numbers together. I could have done it as a long string. I just wanted you to see things are represented that way. Now these numbers, if I were to say highlight them in yellow, these numbers are numbers you're going to see again. You will see multiple situations where these numbers pop up. So we're not going to focus on them right now. Just, notice them. Notice that they exist. When we're doing subnetting, these are going to be important numbers. You can always figure them out by adding them up, but it's also helpful to recognize them and, not necessarily memorize them, but recognize them. So if you see you added the first 3, you got 128, 192, 224. So now let's just do this conversion a couple of times to make sure you're clear on that. So we get rid of all of our values. Now if we wanted to add a 1, a 0, 1, 1, 0, 0, 1, 0. If this is my number, now I can look at this and say, well, there's a 0 in the 1 position, so that's going to be an even number. That tells me something. I also see a 1 in the 128 position. That means it's going to be a number that's greater than 128. So let's see what that number is. We have 128. We add nothing for 64. Let's do it underneath, because there's a 0 in the 64 position. So we add a 32. And that is 130 plus 30 is 160. So we're at 160. Then we add a 16 because there's a 1. There's a 1 in that position. So that's 176. Now we add a nothing in the 8 position, nothing in the 4 position, a 2. That's plus 2 equals 178. And 178 is our number for this binary representation. So if you're looking at 4 characters, you can really get to the point where you just memorize all 15 numbers. If you get to the 255, you do need to do the math a little bit. And that the math is no more complicated than this. And if I were to say, let's turn that into a 1, that is, we add 1, and now we're at 179. So we can count in binary also. Now let's say we wanted the next number here. If I wanted to say, what's the next number after the 179, after 1011, 0011? Well, the way we add in binary, let's use the marker on that. I say I want to add a 1 here. And it's the same thing we just did in decimal. 1 plus 1 in binary equals 0. And then we carry the 1. 1 plus 1 is 0. Carry the 1. Now we have a 1 here, a 0 here, and everything else stayed the same, 1, 0, 1, 1. So being able to count in binary is important. Let's just go through over here. So I will erase all of this. And okay, everything erased. So if we're counting in binary, we have 1 as our first number. Now, if our second number is 1, 0. Our third number is 1, 1. Our fourth number is 1, 0, 0. And we can continue like that. the fifth number 101, the sixth is 110, seventh is 111, and I would eventually, actually my first number that I should put up here is actually 0. So that's the process. And if we want to look at it this way, we can put zeros in front of everything and everything lines up, and you can see the pattern develop. Now we want a fourth, if we want to represent a fourth bit like we had earlier, we can put zeros in front of all of these just so we understand what they are. And what we do here with the 111 is we say that is the next number after that is 1 carry the 1, 1 carry the 1, 1 carry the 1. We have 1, 0, 0, 0. That's our next number, 1. And if we look at this, 1, 0, 0, 0 is represented as 8. 0, 1, 1, let's just try that again. 0, 1, 1, 1 is 4 plus 2 plus 1 is 7. Now the whole reason that we say 7 instead of 0, 1, 1, 1 is because, especially as you get into larger numbers, it's harder to say those numbers, it's harder to write them consistently, it's easier to make mistakes. So there are times we need to convert to binary, there are times that we prefer to have it in decimal. And that's just the way things are. So 0, 0, 0. So now let's do the other direction again using 8 bits. What if we had a number like 143 and we want to convert that into binary? So what do? We say 143, it is greater than 128. So that means we put a 1 in the 128 and then we subtract. And 143 minus 128 is 12 and 3, 15. Now 15 is less than 64. It's less than 32. It's less than 16. So now, if you think about it, if you remember, you represent 4 bits with 1111 to get 15. So, or 4 bits can represent numbers up to 15. We know that our last 4 bits are going to be 1s, but let's just add them together. So 8, we know we put a 1 there and we subtract 8 and we get 7. Now we subtract 4 because we're going to put a 1 in the 4 position and we get minus, then we get 3. Now we'll subtract 2 because we have it in the 2's position, and we have 1 left over. That means we put a 1 in there. Now looking at the number, it's odd, so we expect this number to be, this last position to be a 1. It's greater than 128, so we expect the first position to be a 1. So that's kind of not a perfect analysis of what we have there, but at least it verifies that things are kind of what we expect. So that's how we got to 143. Now if I do the math the other way, I'm adding 128 plus 8 is 136, plus 4 is 140, plus 2 is 142, plus 3 is 143, and that's what we have there. So this is the process you need to be able to go back and forth on, and it's worth practicing. And all you have to do is say, I'm going to take a whole bunch of numbers between 0 and 255 and represent them in binary. So I put a 0, I put a 1, I put a 23, I put a 55. Just do that a whole bunch of times. And then go the other way. Say I'm going to do a 1, 0, 0, 1, 1, 1, whatever you want to come up with. And even I put a space there. It helps me to see that I'm putting the correct amount of numbers. 1, 1. Keep hitting the wrong keys. So you can just put down whatever numbers you want. Practice going back and forth. That is a critical skill to understand the next step of what we're doing with subnetting. So that video is coming up next. Thanks for watching.